I may have mentioned some of this before when we looked at substation fundamentals. So some of it may be repeated. But we want to look a little more in depth. And I just checked my schedule and realized that I have been running way ahead of my schedule. But I'm sure you won't complain. Just means that you have one less module to worry about in the latter stages. Have you gotten a draft timetable as yet for your assessments?
Yes, sir.
Yes, sir, but there isn't a date for your module.
What do you mean there isn't a date? You mean there is no date on the schedule?
Yes, sir. Just didn't put
No
it in.
date, just
There's
any.
no date on the schedule for your module.
Okay, that's interesting. So when you want it? Do you have everything else on the schedule?
Yes, we'll have everything else. Your module is the one that is in.
So when you want this one? I'm sure you have discussed it.
No, we haven't enough, to be honest.
Okay. Well, it's now, time is it? It's now 7 minutes after 5. You have 1 hour and 53 minutes to tell me. So let's move on. So we're talking about grounding today. And you know, it's one of those areas of power systems, of your power system, that it's important, very important, but you know, we sometimes almost disregard it or consider it, you know, that a thing which is so important, but you know, not much focus is placed on it. And one of the points I want to make is that regardless of how fancy your system is, yes, as the point we're making here, it can be rendered useless without corresponding use or application of proper grounding. And I think it's good that I stop at this point just to highlight the fact that in some jurisdictions, you'll hear the term grounding, and then sometimes I may say earthing. Maybe I'm just schizophrenic, but then again, earthing and grounding are one and the same, okay? Grounding, you'll find that more commonly used in the North American setting, while earthing is more European, okay? So it's one and the same. So that said, in terms of your grounding system, as we're saying here, very important, very, very important, but sometimes overlooked. Even in our residential settings, the normal practice is just to get that rod, and you know, whether you're driving a 6 or a 4 feet rod, and you connect your lug to that and your earth wire to that, and you know, you call it George. That is not always acceptable. I've engaged persons, especially those on the hills, who build their houses on the rock. And being on the rock does have its benefits, but of course, it means that you may not necessarily have proper soil to provide good grounding. So the fancy facility, they can become almost unlivable if you don't treat with that grounding. And so special care needs to be taken to provide that. But from a transmission distribution standpoint, we can have what we refer to as back flashover, yes? Where if you have high foot resistance on your tower, if you have, say, a lightning strike, because the foot resistance is high, it means that the potential at the foot of your tower will then rise. All right? And the towers that we are talking about, of course, are metal towers, yeah? So that will rise and can rise to the point where it is much larger than the phase voltage on your system, which then results in the back flashover. All right. So it's a very important part of your power system operation. There was one of my past major projects had to looked at the earthing problem that persons were having in the Red Hills area, the upper part of Red Hills Road there. And in one instance, and I tell this story every time I come to this point, in one instance, we went to a light pole and we were just testing the resistance on that earth wire. And when we went to the base of the light pole, we were getting fairly good readings. We were getting readings, below 10. But then for that particular pole, there's a wooden structure at the side. Now they use a little metal covering through which the earthing wire goes. But anyway, when we went to the top of the wire, we were reading 700 and odd ohms. So at the bottom, we got nice, beautiful readings. But we went a little higher, we got 700 and odd. Not so much a biggie. Obviously, there was an open circuit on that pole. But what we found out in terms of our research was that the utility company had invested in some grease clamps. Some brilliant engineer who had authority went to some conference or the other and was introduced to these grease clamps. And so he thought it would be good to introduce them to Jamaica, which he did. The problem is, in the area or the country that they were being used, their temperatures are not like Jamaica. So after a while, what happened was that the grease just melted and left the clamp. And so you had two wires dangling. All right. So you had there was that open circuit within the clamp. So the clamp was still there, but there was no electrical connection. So you had all these high resistance joints. And so persons in the Red Hills Road area, in that particular part of Red Hills, were experiencing a lot of damage. So once they see the place looking overcast, they started worrying because the question is, who next or which house next? All right. So in addition to having good earthing, we also need to contemplate maintenance. As we can see, yes, we still have connection in this shown in this diagram. There's still connection. The question is, how good is it? All right, and to what extent would the corrosion that we are seeing here impact the resistance that is determined? So we have here a mat connected. It's connected to a rod. Question is, it's physically linked, but what's the level of electrical connection there? So some of the basic needs that we have to consider for earthing. Right? Why do we need it? Upfront, and it's not about continuity of service, but upfront, it's protect human lives. I suppose to an extent you can say it's for continuity of service, because if you are damaging your personnel, then it's going to affect service, no? So it is a requirement to protect service personnel. Very important, and we look at that in a few. And also, thereafter, we can consider the importance of protecting appliances, etc. It maintains voltages in the healthy phase if say fault is on another phase, yeah, because with that earth point, then you know that the fault current will flow through the earth point. For lightning protection, again, you can purchase the best and most sophisticated lightning arresters around, and have it perched on the highest point of your building so it attracts the lightning wherever it is striking. Yes, but if that lightning arrestor isn't connected to a proper earthing system, then you have just wasted some money. Right? Of course, you know, the other risks associated with the electrical short circuits, etc., are minimized with proper earthing. All right. What I was explaining earlier in terms of the back EMF, I said that it produces that rise in the foot voltage when you have that high current, several thousand amperes from your lightning strike, being flowing through that high foot resistance, then you're going to get a significant increase in potential. Of course, we know that ideally the potential at Earth would be zero. But under these circumstances, with high resistance and that lightning strike, you can get several kilovolts at your foot resistance. All right? And as I said, if that now becomes larger than your phase voltage, then given the difference in potential, the higher potential coming from the foot resistance, then you then have current flowing into the network from the lightning strike. Okay? All righty. And this is just a pretty picture to show you how that comes about. But more importantly, what I want to highlight, we are seeing the grounding network. Right? We are seeing the grounding network. Yeah. But you have here the, let me just change the color there. You're seeing the soil in which it's in, but then you also see another layer above it. Okay? And we'll talk about that in a few, but it is something that you're always going to see in your substation. Right? There's going to see a layer of gravel in your substation, and it is not just for aesthetics or to keep the grass down, but it is to provide additional resistivity, which helps to protect personnel while in the substation. Of course, we have absolutely no idea when a fault will strike or when we will have a fault. And during the fault, you want to ensure that if personnel are in the substation working, that they will be safe. Similarly, regardless of how many signs you put up, you're going to find situations where the high voltage sign is on the fence of the substation. And by the way, when we go to the substation, what you'll see is that the fence around the substation, those posts, the fence posts themselves, will have the grounding mat connected to them. All right, and this also protects not only personnel from the company, but it protects John Public. And what I was going on to say is that irrespective of the number of signs that you may have up, there are going to be persons who are going to be leaning on those fences. Yeah. And of course, we would prefer not to be engaged with their legal representatives, assuming they are still around to be represented. All right. Now, although we have very low resistances within the substation, so the earthing resistance is low, and we look at the standards in a few. Even though we have those low resistances, because we are dealing with several thousand amperes, whether during fault or whether during a lightning strike, you can have the potential at the Earth's surface rising to a level that now becomes a hazard to people who are in the station. Yeah. And we want to mitigate against that. And we're all have different body structures. Yeah. We all have different levels of tolerance to current. So you may have an individual who, and I've seen it before, I've actually stood there and watched a gentleman, you know, in the absence of having a voltmeter with him, went up and used his two thumbs and tested whether or not there was power coming from JPS into the home. Yeah. And surprise, surprise, he actually lived to tell the tale. You know, so yeah. So we all have different tolerance to current flow. But because that difference exists, we have to take into consideration what is happening or what may happen under worst case scenarios. All right. So I may be walking around in the substation with the same gear as a Mr. Buchanan, but because of my close to 300 pounds, right, and Mark's thicker skin, you know, it may not affect me as badly as it would affect him, given his very frail frame, you know. I'm joking, Mr. Buchanan. I'm joking. But anyway, you get the point, right? Different people will respond differently to current. But we try to focus on what we refer to as tolerable limits. What it is that the normal person can withstand. Okay? And that is taken into consideration when designing our earthing system. Okay? And so we then talk about what I refer to as your step and your touch potentials. Right? What are these tolerable values that we need to consider? All right, again, just to lighten the mood, yeah. This is not my drawing. Yeah, I got it from Circuit Globe. Maybe that's why it's that pretty, right? But the idea is, what is that current that can flow? And note, I'm using the term tolerable, yes? So it's a tolerable current that can flow. So here we have a situation where if we have a current, a fault, and we have a properly earthed system, then the fault current will simply pass through or flow to our earth system, and somebody working in the substation will be fine. Okay, now that is Circuit Globe's version. My version, and the best I could do, is as shown. So for your touch potential, this is what we have. All right. So within the substation, what we are showing, and the assumption here is, and to be honest, nobody really stands up like this in a substation. I don't think we are all this disciplined. But the assumption here is that both legs are together. So we are standing at attention and we are touching the piece of equipment, right? Nobody stands up like this, okay? But that is the principle on which the touch potential is based. And so what we have here is the foot resistance, because they are close together. The assumption is that they are close together. Then the total foot resistance would be RF over 2. So it's 2 equal resistances in parallel. That's what we are considering there. Yes? And RB here represents the body resistance. Good. And RG1 and RG2 represents the tapped resistance from the equipment up to the point at which the person is standing. I'd say it's as if you have separated the resistance up to where the individual is standing, and beyond that, to where we'll have earth fault current. So if this was in place and we're walking around and we touch the equipment, we provide an equivalent circuit to what we have here. And again, remember, feet are together. That's the assumption. But we know that that doesn't happen. Anyway, so the equivalent circuit would then look something like this, where we have our RG1. Over here would be a RG2. Yeah. Here we have the foot resistance over 2 in series with the body resistance. Right? So the body resistance of the individual and the current, we have the fault current there. But don't focus too heavily on this. Yes. We're not going to ask you to do circuit analysis on this. What we're more interested in is how to determine what is that tolerable current, and by extension, what we refer to as the touch potential, and tolerable current when touching an equipment during a fault, and the tolerable current while walking around in the substation during a fault. So this is for your touch. Oh, by the way, did I tell you that this is already uploaded in Schoology?
No, sir. No, you
don't. That's why I was late, because I was uploading. All right. So you don't have to have your fingers burning. You can just make jottings. All right. Okay. So for the step potential, no, we are being normal. We are walking around. So in stepping or walking around in the substation, we then have a portion being tapped off, separated by our feet. Yes. So we have the 2 feet resistance, RF and RF, and we still have the body resistance. Yes. And the idea is what will flow through our lower body from one foot to the next while we are walking around. Right? Because only your feet would have been connected to ground. Right? So for this, the equivalent circuit looks like that. But as I said, the equivalent circuit is not our focus, nor is the drawing. What I want to simply highlight with these is the fact that we have to give consideration to them. That is the key. You have to give consideration to what happens when somebody touches a piece of equipment during a fault. What happens when a person is walking around in the substation during a fault? And of course, we can't tell, how long or when the fault will occur. We have looked at our relays and we know how our relays operate, and depending on the type of fault, we still have a few things to look at, in terms of protecting the different pieces of equipment. But the reality is, whatever fault it is, it can occur. We have talked about, face to earth faults. They occur. You will have these earth fault currents happening in our system. How do we ensure that people are not at risk? That's the key. So, what's the consideration? As I said earlier, we'll have this variation in terms of what impacts persons. Now, this seems very small. I'm sure if you are an engineering student worth your salt, you would have had experience with currents higher than this before. All right? If you have not been shocked before, then it means that you are completing your degree without proper experience. All right? You need good experience from some electrical drill, or it means that you simply have not been experimenting enough. All right? No, I do not take any responsibility for anything that happens to anybody's home, but I'm just simply saying you have not been exploring enough. All right? And I trust your parents are not listening. But moving right along. All right? We say that 10 to 25 milliamps is enough to produce lack of muscular control. And when I was a child, we simply said that this is when the current hold it. I'm sure you have heard that term, unless you're all from Kingston, which for your sake, I hope you're not. But anyway, as a good country boy, you know, we used to hear that term, the current hold. Yes? So this sort of current then produces lack of muscular control. And so persons coming into contact with these systems at this current level may have issues releasing themselves from the current producing system. But again, it is small. But we're not looking so much even at the magnitude. What is also more important is how long you're exposed to it. And this now comes back to a couple of things that we would have looked at before. All right. So, yeah. This is when you're getting nicely shook up. And, you know, we can have burns from current. You know, that's, of course, a lot more severe. Good. And, you know, it goes without saying. We just have to manage how much current we're going to allow to pass through our bodies. Yeah? Okay. As I said just now, while the current magnitude is important, of equal or even greater importance is how long the current is allowed to pass through the individual. And we have to manage that. All right? We have to manage that. Okay, then. Now, how do I determine, or, you know, where do we determine this time? And how is it managed within the power system? Now, I won't say unfortunately, but the reality is we have not looked at clearing time for faults, right? So we have this concept known as critical clearing time, right? Now, the critical clearing time for a fault is the maximum time that a fault can remain on the system without you having, without you losing synchronism from your synchronous machines. Now, this critical clearing time will dictate the sort of operating time you need for your protection system. So let's back that up. So if I have a fault on my generator, and the critical clearing time for that fault is, I'm just pulling a number, let's say 500 milliseconds. Yep. What it means is that the protection system that you will have, right, in terms of your relays, your breakers, all of that, it must ensure that the fault is removed from the system long before 500 milliseconds. Because if it exceeds that, if the fault stays on the system for longer than that period, then it's going to impact your generator. And once you have a generator pulling out, it's going to impact the rest of the system. All right. Now, you would have heard recently there was a complete system collapse in Trinidad, right? Now that is something that really is unheard of, or it should be unheard of, really, all right? Because they operate a system where the utility company basically provides generating resources or fuel to the generators. All the generators do is to produce the electricity and sell it back to the company. So when that happens, you know that there had to be significant system failure. And it's just that a fault wasn't cleared in time. And it just escalated until the entire system was out. And again, if you can find that news report, you don't even have to go to the technical report. Go to the news report, and you'll see that it took up to 6-7 hours for persons to be restored, for the system to be restored, and for some persons to get back their supply. Well, this is something that we spoke about theoretically in power systems. But if I want you to read that report, and you can get us a better sense of the practicality or the reality of it. You with me? And I'm also saying that, you know, all of that could have been avoided based on what happened on the protection side. All right. So a lot of money, a lot of effort. And I dare say, I know Antonio is in a space that I may get myself in trouble. So I would appreciate if he was using a headphone. But anyway, be that as it may. The most important people within the utility company are really the people in protection. You know, you have all these systems running, but if the protection system is not removing those faulted areas and doing it quickly and accurately, with all the fancy generation you have, with all the fancy systems you have, the system will continue collapsing, right? And, you know, anyway, he's limiting the things I can say because of his space. So let me move on. Okay? Moving right along. So in terms of touch and step potentials, we have that the body can withstand currents from the expression 116 milliamperes over root T, or 116 over root T amperes. All right. Where IB is the maximum body current in amperes, and time, the duration in seconds. So because I took this information from a non-Black text, right? I took it from a very white text. Now that I'm thinking about it, maybe it was written by the Chinese. What they say is that the standard, this standard that I'm giving you, is based on a person of an average mass of 50 kilograms. Now, who you know in Jamaica weighs 50 kilograms? You'd be a bit hard pressed to find many of those around. Right? So, the standard is around 50. But of course, we go above that. IB, 116 milliamps for 1 second, and 156 milliamps for 1 second for persons in the 150, 160 pound region. Okay. So again, you have to establish this for the worst case scenario. All right. So if you have a small person working in your system, 50K people, right? Then that's a sort of current that they can manage, right? And that is just for a second. Oh, that was just 5 seconds of silence, or about 3, right? So the point I'm trying to drive home is that in terms of designing our systems, we have to be thinking about things like this. How will that system that I preside over, how will it impact someone in the substation during fault? Okay. Any questions? Because I've been motoring on for a little while. Questions or comments? All right. So in terms of the IEEE standard, and in terms of the calculations, right? They use the body resistance as 1,000 ohms, which is why it is popping up here. So that's really the body resistance. Okay. The 6 ROS and the 1.5 ROS is based on the taps. So when we were walking around, we were tapping off that ground resistance. Yes. Where rho is this resistivity at the soil. So the rho S, the 6 rho S and the 1.5 rho S is with respect to what is happening on the soil. All right. Now remember, when we were doing the touch potential, we said that you were standing with both feet together. And so we got RF over 2. Okay. With the step, we now have 2 RFs. So in effect, what we are saying is that with one is a quarter of the other, because you are moving from half RF to 2 RF. So for the foot to foot, you'll get the 6. And for the hand to foot, because you will be dealing with RF over 2, yes, you'd have a half in comparison to 4. In comparison to 2, which is 4 times there. Yeah? So you get the 6 and the 1.5. Right? Where, as I said, rho S is the soil resistivity, and that is measured in ohm meter. So with these being the resistance, and we just established what the tolerable currents would be, based on my earthing system or my grounding system, I can now calculate what the step and the touch potentials would be. All right, so I have the resistance, I have the foot-to-foot resistance, I have the hand-to-foot resistance. Yep. For the potentials, it will be I times R. So for my step, I'd have the 0.116 times R step over root T. And then for the touch, it is 0.116 times R touch over root T. Yes, Mr. Johnson.
Sir, I think there's a variable missing between the soil resistivity and the 6 and the 1.5.
What variable?
The rating factor, that these are like the thickness of the
We don't reach
soil.
there yet. We're not there yet. All right. So these are your permissible touch and step potentials. Now, this is assuming that you have what's the name? No? Homogeneous soil, meaning there's no layer. So it's just one soil type that you're engaging with, which is your rho S. Now, if I were to, which is what Mr. Johnson is alluding to, if I were to now add layers, yes, which means I'm now bringing in other materials to support. And if you recall, when I was showing the tower, I showed it that there's a level of gravel. If I now bring that in, so if we want to increase earth resistivity, the equation is now modified. Right, so we have E step and E touch. So we now have our CS, which is a function of HS and K, which I'm going to define in a minute.
Sir, is it everything minus yes, it's everything minus.
No. That's no, this is not minus. That's a unit in volts.
Oh, okay, sir.
My bad. All right. So now that I've introduced the CS, if we have a CS value of 1, what it means is that there is no protective layer. So we go back to the original equation. And then if CS has a a value other than 1, then we use the following graph. All right. So you can just highlight that in terms of the note. So here for this graph, so with CS being, well, the values of CS are on the y-axis, the value of HS on your x-axis, yeah? So with CS equal 1, K equals 0, okay? And it doesn't really matter what depth you would have buried. Yeah? So if there is uniform soil, no layers, then K is 0. And HS represents the depth or the thickness of the protective layer. K then becomes a multiplier. And K is a function of the original surface material and the surface material that is brought in. All right, so the values of K will be given by rho minus rho S over rho plus rho S. So obviously, if the resistivities are the same, meaning you're dealing with one surface layer, you're not adding anything, then it's obvious that K will be 0, right? Otherwise, it will be one of those negative values that we showed. And since our objective when adding surface material, the objective is to increase resistivity. All right, so you're bringing in material with a higher resistivity because you want to increase the step and touch potential. So for that reason, you're going to end up with a negative value. Now, I think it's important for me to point out that in some instances, when you add material, you're actually trying to reduce resistance. So you're going to use things like a brine pit or well, that's the only one that comes to mind.
Yeah, this gem thing that people buy for lightning protection systems.
Again?
You have gem ground enhancement material. They usually buy them when they're doing lightning protection systems.
Okay.
You can buy it at the hardware.
Yeah. So, and that is to reduce your resistance. Because again, as I said at the beginning, you have the fancy protection system, but if you don't have the proper grounding, you're wasting money. All right. And this is something that is overlooked in many instances until, of course, you have a problem. Okay. So the other thing we need to consider is the allowable earth resistance. And it depends on what we're where we're operating. So there's an allowable earth resistance for a substation, and we looked at the different substation types in power systems. And so in terms of the operation, you would have different standards attached. Okay, so what I'm giving you are very general numbers. And of course, especially where the utility is going. And I hope I have my, yeah. So there are 1, 2, 3, 4, 5. All right, so there were 5 rate categories within the utility company. That is now being reduced to 4. So you have residential, you have commercial, and then you have industrial, and of course street lighting. So the biggest customer for the utility company would be street lights, and they and water compete. But they are now removing, and the reason I'm mentioning this is that the consideration recently is to remove the rate 40 customers. So you now have rate 50, 60, 10, and 20, all right? Now, these rate 50 customers would have to provide their own substation facilities. As a matter of fact, they would possibly have to purchase their own transformers. So they have to run their own substations. The fact is, you may not end up working for the utility, but on the side of the industrial facility, you would have to have an appreciation for what is needed to maintain the substation. Or if you have to create, who to tell, maybe we are in an expansion mode now in Jamaica, I don't know. But, and if you did intend to go to Canada, fine, I'll just hunt you down after a while, but I will understand that you have to leave. But that's it. And I hope I have not put any ideas in your heads, but moving right along and doing so very quickly. So we have, that's your substation. And it's obviously not gonna be, it's not gonna be obvious but you do have that mat beneath the substation. You're not going to see that, but it's there. So you're going to put in a new substation. There are new housing schemes going around now or going up now. And in order to properly service them, people, will need to build new substations. You're going to excavate. You're going to put in your mat, and then you're going to backfill and ensure that your mat is connected to the mesh. And I want to highlight that. Of course, all of this that I'm showing you, when we have our visit, you just make note so that you can try and make the connection between what we're talking about in class and what is actually out there. So you have the mat, but you also have a mesh, which is right in front the various pieces of equipment in the substation. So when you go to a substation and you're working in a substation, added protection, even though the calculations have been done in terms of touch and step potential, and yes, you need to wear the proper shoes and all of that. Yep. The fact is there are other safety features. So there's a mesh that you're required to stand on, and it's always right in front of the equipment. So you stand on that when you're touching. I suppose if we take that into consideration, then the feet together that we mentioned earlier with the touch potential may not be so far-fetched after all. Yeah, because the mesh is really small, right? Okay. So in terms of the resistance values that we have to consider, so for residential, we can deal with the 25. And this is usually easily achieved by just driving a rod, right? So you have your 6 or your 4 foot rod, 4 feet rod, you drive them, put on your nut and make sure it is tight enough, you're good. Light industrial systems, you're dealing with 5 ohms. Once you start talking about substations, right, whether it is for an industrial facility or whether it is for the utility company, we're talking about 1 ohm. So it needs to be very low, okay? And you're gonna have to then do what is necessary to try and achieve these readings. Because remember we mentioned before the sort of ground potential rise that may occur. For the others, in terms of the industrial and the residential, these are not considering lightning strikes, even though that is a possibility. So if you are going to, when you decide to secure my pension and you build all of those things on the hills, all right, when you build on the hillside, and you need to be conscious of the sort of lightning activity that takes place in that area. A lot of persons don't really give much consideration to that. As a matter of fact, if you think about it, but then again, you guys were too young, you wouldn't even have been giving much thought to it. But in St. Anne, was it in Monique, where they had all that flooding and you had these ponds popping up. In Manchester, we had quite a bit of rains a few years ago, and they had waterfalls in Porus, and massive flooding in Porus, where we had to raise the level of the road several feet. I mentioned these things because these flood events seem to have taken many persons by surprise. But the truth is, these aquifers have always been there. Many of the areas that we build in were waterways. We just kind of ignored it and built anyway. I am now saying to you that one of the things you need to give consideration to from a protection standpoint is try and get your hand on what we refer to as an isochronic map. Right? An isochronic map gives you an indication of the lightning activity, yes, in an area. So you can know from, across Jamaica what areas, if you have a customer who is going to build in that area and may not be familiar with the area, based on the isochronic map, you can say, well, hold on, there's a lot of lightning activities in that area. Therefore, having built it, you need now to put in the necessary safeguards against lightning. You understand what I'm saying? Huh? So I just throwing that out there. And then when you go on the job and you give these considerations, they realize that you actually went to school. So here we are now, just showing the different parts of your system. So from generation, so from the power plant, you have to think about earthing. You're on the transmission system, you still have to think about earthing. You come into the substation, from the utility substation, you still have to think about earthing. All right. You come down to a small transformer going into an industrial facility, still have to think about earthing. You're coming on the road, on the distribution system, at the pole, you still have to think about earthing. And you come into the residence, you still have to think about earthing. And don't be bothered by this. It's just that the assumption is that you're in a built-up area and therefore your distribution is underground. That's why we put the transformer underground. But in our cases, many of them are pole mounted. Okay? But the fact of the matter is we have to think about earthing or grounding right across the power system. So wherever you land, give some thought. So showing some connections, interconnection in terms of your earth rods, tying them together. Okay. And of course, there may be a mat underground. This one looks like something that would be for, a residential area. No, actually it's not. It's more industrial. Okay. But if needs be, as simple as that is, very effective. So you have rods at these points, and you're tying them together. All right. Okay. Okay. So as I was saying earlier, from your simple system, you have most of them, we have simple rods connecting them, and the number of rods along with the type of soil that we are using will determine your earth resistance. So in the great parish of Manchester, yeah? Oh, come on, you find nice alluvial soil all over the place. You grab a rod, you drive it, you're fine. You go to Clarendon, you have clay, you go to Westmoreland, and I only recently learned that some persons are from that parish. But anyway, you go to Westmoreland, you have your clay, you might be good. But then you come to St. Andrew, you go in Red Hills and it's pure rock stone. Question is, can one rod provide the sort of protection that you need? All right. So we may have one circular rod, and if we have one, then the resistance, and I'm not expecting you to remember these formulae, so the resistance will be given by that. If you have two, that's the equation for the resistance. That'll be an interesting equation for you to use in an exam. What do you think? But anyway, so whether you have one or two rods, yes, That's what you'll be seeing. Okay. And for the two rods, the assumption is that the length, yes, or the for length B and radius R and spaced by S, where the length, yes, is much smaller than the spacing. So B is much smaller than S. Right? Then we have, oh, beautiful. Yeah, yeah. But as I said, we're not here to ask you to remember these formulae, right? I want you to appreciate the concept. And of course, if it is that, you have interest in doing work in earthing systems, then of course, if you're writing, programs that would do some calculations for you, then you would have to have an appreciation for these formulae. You with me? If you're going to do the in-depth analysis. But for our purpose, what I'm trying to get you to understand is that it's not just about getting two rods. So let me back it up and say it differently. You have one rod, you get a certain level of resistance. Just simply getting another rod and driving it may not necessarily achieve the goal that they are seeking. You have to consider how far apart you're going to put those rods. Because driving them next to each other will not improve the situation. You with me? So you have to give consideration to the length of the rod, how far apart you put them, etc., etc. All right? You can also use a grid. So the easiest one that we mentioned just now, your rod. Drive your rods, link them, tie them to your system. Or you can use a grid. Right? And this is designed firstly to ensure that your step and touch potentials are within the acceptable limits. Right? Now, once you have designed your grid, you can then use some rods, right? Having designed it, you can then make adjustments to the spacing. So because you are making several changes in terms of your analysis, right? Right? In terms of making changes during your analysis and calculating the resistance, right? You have to then, it's going to become a complex task. And so, computer analysis may be necessary. I'm going to ask you to excuse me for a brief moment, all right? I'll be back in a minute. My apology. Wow, I see you all took the opportunity to run away. Was it that painful? Eh? Miss Gray?
We're still here.
All right. So we're saying it's a complex activity, and therefore the analysis we done by a computer. Okay. However, I'm gonna go through basic exercise to try and outline the process. Okay. But even though we may use rod or we may use mesh, it always comes back to the soil in which we are going to bury this. Okay. Moisture in the soil is going to impact your resistivity. All right. And of course, if you can't determine that the moisture is consistent in terms of spread throughout the system, it's going to impact it, or it's going to vary depending on the level of drying out at one point to the next. So as part of your overall analysis, you may end up using average values for the type of soil that you're using. All right? And we have some standard values, okay? And note, we have that range. So you look at the first one, we're ranging from 590 to 7,000. Right? So what we focus on would be the average values. So these are the resistivities. And if you note for this one, we have crushed rocks, gravel, sand. Yeah. This is what you'll find in most substations because this has the greatest impact in terms of increasing resistivity in your station. All right. Okay. And I hope we have carefully, or should I say accurately, understood what we mean. And I kept using it because I kept telling you that it was a tolerable current that we were dealing with. All right. So we're talking about the tolerable step. If your step potential, when we determine what our step potential, our tolerable step potential is, what that means is that once you have that step potential, it will result in a tolerable current given the average resistance of the body. You with me? So always remember that step on touch that we're talking about is a tolerable step on touch potentials. All right. So we're going to use our mats where we find that the rods may be ineffective, right? And a mat is simply, some meshes, where we talk about meshes, but anyway, some meshes buried at a certain depth. Okay? And our task as engineers would be to design that mesh so it produces that earthing resistance that is acceptable, meaning it will produce a touch and step value that is tolerable, that results in a tolerable current. So the task then is first to determine the material, the spacing, yes, the number of meshes in our mat, and then determine how deep we are going to bury it. So we are looking at the grid, right? And we are looking at how far we are going to bury it. So we have here a little figure. Nothing fancy about a mat with 9 meshes. Well, we have an area, W squared, where the area, or should I say the width, is much greater than the depth to which you are going to bury it. All right? And we have a figure which compares 2RB over A. Don't ask me why 2RB over A. That is what I'm giving. In other words, there's no great significance to it. If you go back to the formulae that we were looking at, right? These are values now that are considering the depth, the area, the corresponding radius, etc., etc., etc. Right? So it is 2RB over A and pi WR over rho. So it's taken into consideration the depth, it's taken into consideration the area, it's taken into consideration that big R, which is an equivalent R, and it's taken into consideration the resistivity of the soil in which you are going to bury it. So these two are compared. All right, and from that we can then determine whichever of the parameters. All right, so here is my mat. All right, so that's my 9 mesh mat. All right, 3 by 3. And from my 9 mesh mat, we have the width of the mat. Yep. Nice and square. This is the graph that we're saying we are comparing. So you have the 2RB over A and the pi WRP over P. And then we have, these are just plots in terms of the two. And this lower one is for the 9 mesh mat. This one is for the 4. And that would be for the single mesh mat. All right. Okay, so in terms of what we have here, the R, big R, is the required earth resistance in ohms. And rho is the resistivity in ohm centimeter. And then here's the example that you're going to go through. All right. So based on what we have here, 20 feet in terms of the width, equivalent 6.1 meters, buried 1 foot, consisting of rods of a 1/4 inch. And of course, that area would be 37.2 meters, which is 6.1 squared. All right. So if we were to substitute those values and then look at our graph, which we had shown earlier, yes? So if input those values to get our 2RB, then 2RB over A would be equal to 1.03 times 10 to the minus 4. All right, so it will be 10 to the minus 4, which is there on the 2RB over A. All right. And if we were to use a for the 4 mesh mat, it would produce on the y-axis. So if I were to know, after getting my 1.03, yes, if I looked at the 4 mesh mat, so this is the 4 mesh mat, then it will be coming out somewhere there. Obviously, it's a little less than 0.1. If you go straight across, are you following me? If you're not following me, just put up your hand. And let's go again.
Do it again, sir.
Are you following me? Okay, so here's the question. Here's the question, all right? That's the question. So what we're saying first, you have the width of the mat. All right? You have the radius of the rods. Okay? You have the depth to which you are going to bury it. And the 6.1, the area, the width, corresponds to an area of 37.2. So if you substitute into the 2RB over A, R the radius, B the depth, A the area. All right, if you substitute that, you're going to get 1.03 times 10 to the minus 4. All right. So if you then go back to your figure, 10 to the minus 4, all right, we have, this is 1 times 10 to the minus 4. It's obvious we can't estimate the 0.03. Okay? So if you move the point, on the 1 up to the 4 mesh mat, what we can say is that it would come out somewhere here. It will be less than 0.1. We have 0.08 here. Between 0.08 and 0.1 is 0.9. 0.09. Okay? So obviously we can't really estimate it, but I am telling you, I mean, given my excellent eyesight, I'm telling you that it is 0.097. You can't estimate that. It's 0.097. Yes. So we now have the y-axis value. But the y-axis value based on what we have here is 6.56 pi WR over rho. And what we are interested in is finding R. So now that I've gotten the y-axis value, right? Well, now that we have the y-axis value, I assume that for 10,000, we can look back at our table. So let's see what is in the range of 10,000. I didn't realize it was this far back. Okay, So for 10,000, we may be operating in either clay, shale, loam, but that would be at the high end. But since we are using average value, we may be operating in a sand and gravel mix. You with me now? So this may be the material that we are burying our mat in. So we assume that 10,000 for row, and given that row value, because we now have row, we already have W, and we know what pi is equal to. When we substitute the 10,000, we're getting the earth resistance to be 7.7 ohms. So I use the format, yes, the 4-mesh mat. I bury it 1 feet. It is 20 feet by 20 feet. It only has 4 meshes in it. I put it in the gravel mix, and I get a 7.7 ohms. I go back and I look at my table in terms of acceptable values, and I see that 7.7, yes, it is much higher than what I would need for a substation, but it is okay for an industrial facility or commercial facility. Because the light commercial or light industrial requires 5 ohms. But I'm getting 7 by my design. Okay? If I'm not satisfied, or this could be a fairly good trade-off in discussions with your manager. But you can say, all right, tell you what, let us use 9 meshes instead. And if I use 9 meshes, I know come down to 0.09. Yes? And with the 0.09, based on the mix that I have, I may come down to 6.5 ohms. So I would have a new value on the y-axis. I come down to that. The alternative, however, the alternative is that we could find a smaller value for rho. So let us say there was a construction site next door, and they had dug up all this this material, nice, lovely dirt, and they really wanted to find somewhere to dump it. The thing is, it is better than the gravel that you have. So you'd bury it in the dirt instead. So you'll have a win-win. They find somewhere to dump their dirt, and you find good dirt. So your resistivity is now lower. With a lower resistivity, it means that the earth resistance would also be lower. Is it clear now? All
Yes,
right.
sir.
Yeah, so the point I was making earlier, for a light industrial system, you have your 5 ohms, and we can work with that. So the 7.7 is okay, but if you want to be on the safe side, then we make the adjustments to ensure that it goes below that. Yes.
I can go. Oh, yes, sir. The formula that we get, how does it factor in like the like for this? Did it assume how many rods did it assume was there? Would it be 1?
It wasn't a rod, this was just a mesh.
Oh, so when it says consisting of rods of radius.
That's what you use to make the mesh.
Oh, the rods make the mesh. Okay.
Yeah. So you're making the mesh out of these rods with that circular measure. So the other option is, okay, you have gotten down to 7 ohms. You can then tie that mesh to two rods. So you put two rods in and measure your earth resistance.
So if you were using, for example, like the copper wire to do this, you would just use the radius of the copper wire
Yes.
or some. Okay.
Yes. Yeah, as a matter of fact, I'm quite excited about this, because when I left CAS, this was one of the first projects I was thrown into. At that time, I went into telecoms, and I was thrown into the project. We were in I was working in Mandeville at the time, and one of the issues we had was that every time that the clouds got dark, we would be fretting, because Huntley, one of the highest, one of the high areas in Manchester, and regardless of which radio station you listen to, they have a transmitter of Huntley. All right. Once it got overcast, we started worrying because Huntley was gonna get hit by lightning. All right. And the earthing project was something that I was sort of thrown into. So it's very exciting, and it's very rewarding to see that when you improve that and you go and you measure the earth resistance and you improve that, you can see, solution, right? Okay. I thought that this was going to be a short class, but anyway, sorry. Yeah, I chat a lot, I know. Anyway, so we need to meet touch and step potential. Yes. If we need to do that, then we need more in-depth analysis. All right. We need to know the number of rods, the soil that we are going to select, and if we put on topsoil and that, etc., etc., etc. Right. So, once we start focusing on the step and touch potential, we know that we're going to have, I say, a multidimensional problem, which requires computer analysis. But note, students, I'm not asking you to go and learn how to do the design right now. Right? I think there's a program I had shared. I will try and find it and give it to you. You can use it in the future. But note what my objective is: to give you an appreciation for what goes into the analysis. All right? Is your hand still up, Mr. Johnson? All right. So it's to give you an appreciation and for you to make the link between what we would have done in power systems in terms of the fault analysis. Why is it that you need to understand fault analysis? Why is it that, unfortunately, you haven't done stability? But, we would think about system stability in terms of why is it that we want to get the fault off the system, But be that as it may, this is for you to appreciate the process. All right, so this is the sort of information you would have had. All right? You have the substation, you know what the system voltages are, you know what the short circuit capacity is, and of course, you know how to determine the short circuit capacity, right? Because you would have done that in your fault analysis. Remember when you found the short circuit capacity for the bus bars in lab number 1, fault analysis lab? Am I back into the room by myself?
No,
Yes,
sir.
sir.
Oh, you all remember? Beautiful. It's the same thing. That's the information you would need to do. So you'd have the system, and the systems that you would be engaging with. They have models of it. So obviously you wouldn't be doing it on the actual system. But anyway, be that as it may. So you have the short circuit capacity. You have the area in terms of the substation area, the size of the station you're going to deal with, right? The 250 milliseconds is estimated for earth fault maximum clearing time, which you would have done or you would have determined using your stability analysis. Okay, so that would be the maximum clearing time. How long can you have the fault on the system without you having the system dropping? You have 100 ohm meter at the site, relatively low, but that's what we have. And the contractor has access to some crush ducts, which should give you an additional 2,000 ohm meter for a depth of 0.5. Right? So these are some of the, this is some of the information that you would have had and you know what you have to work with, okay? Now, it's multidimensional because the question Mr. Johnson asked in terms of when I mentioned the rods being in the mat, and he's saying, well, if I had copper wires, could I use them? I said, sure. But of course, you need to bear in mind the diameter. Here, you have to start from that premise. So the size, unless you are going from practice, meaning that there are certain, you would have, for use of a better word, local knowledge. Yeah. So, I mean, Jamaica is not a big place. So there would be some local knowledge in terms of the type of the resistivity that you're going to experience in certain parts of Manchester, certain parts of Kingston. You with me? And so in designing, substations are already here. Substations are already on the very sandy soil in Kingston. It's already in the red dirt of St. Anne and Manchester and Clarendon. It's already in the clay in Clarendon. It's already in the clay in Westmoreland. So you already have that local information. So you know the type of rods or the type of materials that you would have needed to use. So this example, what we are saying is, okay, let us say that we are using copper clad steel wires, and this is the diameter, all right? And these have a maximum current carrying capacity of 15 amps per square millimeter. And that is up to a 30-second duration, right? You can then look in terms of the time that we were considering. The maximum time was 250 milliseconds, yes? If these can carry up to 15 amps per square millimeter for 30 seconds, then, you know, if it can carry the maximum current, we're good. The mat won't be converted into a fuse under fault. Because if the current carrying capacity of the mat, the material used to design the mat, if that is too low, then it's just going to melt it. All right? So these are some of the things that I'm saying. We're making assumptions, but you would have this information. For the fault current, we know it was 2,000 MVA on the 132 volt side of the system. Yes. We would have gotten that at the bus bar. Yep. So we know that the fault current would be 8.74 kiloamperes. Yes. And that's a three-phase fault current. Yeah. Giving a corresponding current capacity of 12.36 amperes per square millimeter. So we know the area. We know since we have the diameter of the wire that we have available, we know the current that will flow. so we can test the current carrying capacity required. In this case, it is 12, and we know that this has 15 up to 30 seconds. So having done that test, yes, having done this test, we know that the available wire can handle it, the fault current. And it will handle it for 120 times the time that we expect the fault to exist. Because we need to clear it by 250 milliseconds. So it will be 4 times the 30. So we can have, so we need it 120 times. We're good. That's the point we're making. And then we find the step and touch, 371. That's the top. These are the tolerable voltages based on the soil that we have. So we have 100. So that's fairly low, right? But it is what we have. This is the area we're in. This is where the people are living. We can't tell people to move because we can't find a suitable place for them substation. We're just going to have to find the solution. All right? The people build them houses there. They build their communities there. We need to go and provide the power. Given the space that we have, right? We know we are covering an area of 20 by 20. We have the total length, right? We are crisscrossing, yes? That's 2 by 20 by 100 to give us 4,000 meters. And the area, total ground area, I said 20 by 20, no, it's 100 by 100. So because we are spacing them 5, we have 20. And yeah, right? So we're spacing them by 5 meters. So that's where we get the 20 from. But we are doing 20 for 100 meters. The total ground area would just be the 100 by 100, which is 10,000 meters square. Now the formula that we're using is a simplified formula from what I had shown you earlier, right? So that nice long formula that I told you should have, I'm joking. I said you didn't have to consider, right? This is a simplified formula. So you're gonna be using the resistance being equal to rho over 4R plus rho over L. All right, and then we define all of these, where R is the grid resistance in ohms, P or rho, that's supposed to be rho, the soil resistivity in ohm meters, R the radius of a circle equal to the grid in meters. All right, so you have a circle, right, which is the same area as the square grid. So the square grid is 100 by 100, 10,000 square meters. We're gonna find the radius of a circle which has an equivalent area. So that's for that R. And L is the total length of the grid conductors in meters, which we had already calculated. Okay. So we make the substitution. Again, remember, I'm not asking you to do these calculations. What I want for you to do is to appreciate the concept. All right. So we make the calculations. This was our 10,000 was the area. What we are doing here, it was calculating the equivalent R. It's rho over R and rho over L. Right? So of course the area will be pi d squared over 4. So I'm just rearranging that to get 4 times the square root of 1,000 over pi. All right. So we get R using our math, our design, 5 meters apart, okay, using that particular conductor size or rod size. Yeah. Now, with that R, considering what the touch and step potential are based on the short circuit current that will be flowing, because now that current, because remember, we're diverting all of that to earth. That's the hope, at least. So if we divert that to earth, it's going to flow through the earthing resistance, which is what we have calculated. So having calculated that, the potential rise, the ground potential rise, is 4,091. Oh, this is significantly higher than the tolerable step and touch potentials. All right. So what we do, we apply some diversity factors. All right. So we apply some factors to this. And the current diversity that we have here is quite similar to the diversity factor that we'd apply in your installation, where you assume that not all the load will be on at the same time. So there will not be equal distribution across the mat. That's what you're hoping. So applying that type of principle, yes, we get that 60% GPR, we go out to 2,454. All right. There's another thing we mentioned in terms of the end mesh criterion. Again, you don't have to worry yourself too much about that. But if we apply that other factor, we bring it down to by 20%, we still at 490. And this is still higher than the step and touch potential. So the question is, what then do I do? Right? We can repeat this process. Yes. We can increase or reduce the size or the distance between within the meshes. So we had them at 5 meters apart. We can now bring them closer. That's one step or one approach. We can put in the rods. So here is where I now need you to focus. So we have gone through the process using the formula, and note I used the simplified formula. Yeah, it's a little more detailed than that, but we'll put that in. We'll get all these values. We'll get the mat resistance. We'll consider what the fault current will be, the maximum fault current possible, and then we apply the factors. We see what our E-mesh is. We see whether or not it is okay in terms of step and touch potential. If they are not, then we can use them. So we look at other solutions. And these are some of the solutions that you would have to consider. One, change the spacings. If we reduce the spacing, it means that you're now going to be using more material, of course, but that will reduce the resistance, and hence it will reduce the GPR, the ground potential rise. That is what we are trying to reduce. Yes. We can accept the crush rocks from the contractor. So if you put that in, it means that it will now increase the tolerable touch and step, because it will now bring in a higher CS value. Yeah. So you now get that multiplier effect, because the tolerable touch and step will increase. Okay. Increasing the tolerable step and touch voltages will now produce or allow you to still maintain the tolerable current with a higher resistivity beneath your feet. The E touch and the E step increases, but it still maintains the tolerable current, tolerable body current. You with me? So I'm better if it's, you know, it's a trade-off. I'm walking on dirt or I'm walking on crushed rocks. On dirt, the tolerable step will be lower. But I use the crushed rocks, the tolerable step now increases, but it still maintains the tolerable current. All right? Okay. And then the last one we have here, use the rods at the side. So we can, you know, drive some rods to reduce the resistance. Once you put in those rods though, you now need to measure resistance. So in terms of the design, we would have been able to calculate the resistance. When you put in the rods, you know, measure the resistance. All right? And then finally, reinforce the mesh with grounding rods would bring down your E-mesh significantly. All right? You would need to use your crushed rocks, but then again, it won't hurt. So what I'm going in applying the second solution, which is to increase the soil resistivity with the crushed rocks. All right, so the solutions I gave you here, the options, is to redesign. So it means that you're going to need more material, you're going to need more wire, you're going to need, yeah? If you bring them closer together. You can use the crushed rocks, which increases the potentials. Or you can reinforce the mat with your rods. And if we apply the second one, which is to bring in the crushed rocks, we now get an overall resistivity of 2,000. The E step goes up now to 3,000. The E touch increases to 928. But then look at what happens to the mat resistance. All right, it goes up by almost 20 times. So it means that the ground potential is now 49 kilovolts, and the E-mesh, when you apply all the criterion that we just mentioned, comes down now to 9,000. Okay? Which again highlights the fact that this is a problem of optimization. All right? So, guess what? It is 1:51 in terms of minutes we have been talking. I am hungry. I'm going for my dinner. Oh yes, this is being recorded, no? Anyway, it is at this point that you need to tell me the date you're on the exam.
I think the 26th would be good, sir.
26th of what?
Of
Bro.
April.
26th of April?
Yes, sir.
What day is that?
So Tuesday.
Tuesday. All right, what time? Don't be shocked. I know it doesn't sound like it's Isaac talking to you, but it's hard. Strange things do happen. 26? What time? What time you want?
Sir, during the regular class hours, that's fine.
All right, 5 to 7. All right, that's it. Write it down on your timetable. And I'll make it happen. All right?
Okay, sir. So
Okay, sir.
All right, so we have a date Saturday, no, sir? Oh, not Saturday, next week, Tuesday. Can I have a date next week?
Yes, sir, mid-semester.
Just to make sure. You know. right? And then we have just a couple of things left to do. We have to look at transformer protection, which is quite simple. That's something that you would have already done in machines too. And then we wrap up with generator protection, right? Using a generator transformer. And that's it for protection. Right? I know it's an intensive module. I know it's a lot of reading, but you know, I know it well for me it's rewarding, you know, for me. So I'll continue to reward myself. Have a good evening. Take care. All the best. Depending on how I feel tomorrow. No, that's not true. I have some meetings tomorrow. Yeah, I have some meetings tomorrow. So we'll see what happens, depending on how I feel after the meetings. All right. I definitely need to go and edit this tape. All right. Have a good one.
Alright,
Thank
later,
you,
sir.
sir.